frustrated state. So for this system, it might be pretty frustrating, but for us, it's actually pretty interesting. So going into the objectives, or going into why this is actually pretty cool, is because this frustrated system has actually been a point of intrigue for physicists for decades. What is also very interesting is that because you have like this geometrically frustrated state, your electronic and your magnetic states are in this kind of correlated system, in such that you alter the electronic state of a material, you also alter its magnetic state in response. And so you can tune these electronic and magnetic states to like have this kind of configuration that you want to have, which is very useful, especially for quantum computing. A previous study at Harvard and MIT in 2018 actually studied iron-2 stannite, Fe2SN3, and what they found is that the particles over there travel at nearly the speed of light. And so what this means is that in quantum computing, there's this principle known as the decoherence principle. And the amount of time it takes for you to observe a quantum mechanical system results in some information loss from that system traveling to the observer. If the particles travel at nearly the speed of light, there's actually minimal information loss. So in like a material such as iron-2 stannite can be somewhat comparable to that of magnesium nickel phosphide, and it's also a promising field to study. With that in mind, the objectives of this study are threefold. We first aim to determine an efficient pathway to synthesize powder and single crystal forms of pure magnesium nickel phosphide. We want to synthesize the powder form simply because it's simpler. If we have the powder form, we can then perhaps use it in future studies by which we can create larger macroscale crystalline forms of magnesium nickel phosphide. Additionally, we want to try and form single crystal forms because if you have a polycrystalline material, such as like, I don't know, like you take a bunch of crystals and they're kind of just stuck together in different like orientations, you have a lot of confounding variables by which it then makes it difficult to do any sort of measurements. However, having a single crystal form has only one single crystallographic orientation by which we can measure intrinsic properties of said material. We then want to characterize this crystalline structure, determine whether or not it actually conforms to what we predict the material to be, and then finally observe and explain the presence of exotic quantum states, as I mentioned earlier. So for the powder synthesis, we first take stoichiometric, or a 2:3:1 ratio of magnesium to nickel to phosphorus. We grind it for 10-15 minutes in a mortar and pestle. Once we put it in our mortar and pestle, we put it in a quartz ampule, by which after that we vacuum purge it to prevent any sort of gaseous media in our tube, because in the subsequent step, which we heated, the gaseous buildup will actually cause the tube to explode, right? So you don't want any sort of gaseous media in your tube. Then we flame seal it such that this tip is kind of closed off and it more or less looks like an elongated pill. And then we subject it to a heating cycle. And this heating cycle, I want to emphasize, is very trial and error. I've done more than maybe 40 samples at this point, and each of these have had to like modify the temperature and so on and so forth. But for the purpose of time and for the sake of simplicity, I want to just talk about two of these methods that I've used that yield the most promising results. Firstly, we first ramp it up at a very slow rate, because if we ramp it up higher, phosphorus actually has a tendency to sublime, which means it goes from the solid state to the gaseous state. If it goes to the gaseous state very quickly, you can have pressure build up, once again causing the tube to explode, and you don't want explosions to happen. So if you heat it up very slowly, you allow enough time for like pressure equilibrium, kind of like just allowing it to settle down. We then leave it at 400 C to kind of kickstart the reaction to go in the first place. It's kind of a driving force. Then we heat it up again slowly at a higher temperature to allow the reaction to go on forward. It's like pushing it forward. And then finally, once this heating cycle is finished, we then take out the tube and just leave it in regular air for it to rapidly cool down. Because if you then slowly cool it down, it gives it enough time to form other byproducts which you don't want. And before I go into the single crystal synthesis, it might be useful to talk a little bit about the definition of flux growth. So over here, we are using a simplistic form of a tin-lead alloy phase diagram. And we start at point Z. At point J, this is entirely in the liquid phase. The tin and the lead are completely mixed together in the liquid phase. We then slowly cool it down to about 200 Celsius at point K, by which we have solid particles beginning to form in this liquid matrix. As we continue to cool slower and slower and slower, the solid particles begin to get bigger and bigger and bigger, which is the premise that we want to have in crystal growth. If you cool it more, you then go into the solid biphase region, which then forms another solid within a bigger solid, which is what we don't want. So what we want to try and do is allow for our system to slowly cool from the liquid phase to the liquid and solid phase region to form crystals in a liquid matrix, after which we immediately take it out and get rid of any sort of liquid that's remaining. So with that in mind, we then go to the single crystal synthesis. The initial procedures are kind of analogous to what we did for the powder synthesis. We combine 2 to 3 to 1 ratio of magnesium, nickel to phosphorus. However, in our liquid, we actually use tin as our solvent. Tin has been shown to easily dissolve magnesium, nickel, and phosphorus at a design composition. However, as I showed previously, that was actually a binary phase diagram, whereas over here we have 4 compounds, or 4 substances, which makes the complex, which once again makes us have to use a trial and error method. We then seal it. Sorry, before that we actually add a piece of quartz wool as a strainers, right? So when we separate out the liquid, the only thing that's remaining is our crystal, and all the liquid is actually settled on the bottom. We then seal it, and then subject it to a heating cycle, which I'll be explaining in a sec. And then we centrifuge out, mechanically, any sort of remaining tin flux. And then in order to get rid of any remaining tin that has settled on the surface of your crystal, we then dilute it in HCl. So this is, once again, we have a similar heating cycle, or a similar process. However, I want to emphasize the slow cooling down rate from 100 C, which is everything is in liquid, to 850 C, which is right above that point where it becomes a solid. By which, after we centrifuge it out, and then wash it with HCl and water. So over here we have our products. In our products, the powder form is actually dark brown grayish, it's a coarse texture. And the single crystal form is very small, it's about in the millimeter scale, needle-like morphology, and a shiny metallic gray surface. It's also very brittle, so when we try and do any measurements, it actually breaks very easily, which makes it rather painful for us. And over here we have the powder composition, which we demonstrate. So over here, this is the X-ray diffraction spectrum, and on the y-axis is the intensity, and the x-axis shows the crystallographic angle. And the location and the intensity of these peaks kind of give us an identification as to what our target compound is. So we aim to synthesize magnesium nickel phosphide in a 2:3:1 ratio. However, just because you combine it equally doesn't mean that you'll form your target product. You might form something like magnesium nickel phosphide in a 3:26 ratio. So what X-ray crystallography does is it determines, yes, you have magnesium, nickel, and phosphorus, but in what crystal structure? So what we see over here is that, yes, we have our target compound, but it's still mixed in with a bunch of, or with this other polymorph of the nickel-rich phase, which we don't want. And as transition metal phosphides are insoluble to mineral acids, this makes the separation all the more painful, which means that we have to try something else. Additionally, for the single crystal composition, yes, we have pure something, but it's magnesium nickel phosphide in a 2.5, 11.5 to 1 ratio, which is, once again, not our target compound. So what does this mean? Moving forward, we aim to modify our single crystal synthesis by varying the choice of solvent and adjusting the reaction conditions, such as time, temperature. But the powder synthesis, we're trying to do such that we have nickel 3-phosphide pre-made, and then we add magnesium afterwards, which can alter the reaction and might make it more favorable to form our target compound. Additionally, there's this other method that's been reported in this really old German paper that says we heat it up at this cycle, and then we have another oven that's already preheated for 1000 Celsius. We take it out, we grind it, we then put it in this oven, and then we leave it out to cool in air for a very short time. Maybe it'll work, we don't know yet. And finally, this goes without saying, but I would like to thank the Boston College RU program for allowing me to participate in this wonderful program for another year. I'd also like to thank the TAFT lab in general, particularly Hung Yu Young for putting up with me, and the National Science Foundation for providing us with the funding to do such great work. Thank you.
Time for 1 or 2 questions.
Courtney?
What are the applications for this research?
So like I said in the beginning, well, fundamentally, we do this research because we want to know about these intrinsic properties. We care because it's interesting. However, because we can tune these electronic and magnetic states because they're correlated to one another, this has potential applications in quantum computing. If you'd like me to elucidate this on further, we can talk about this after the presentation. Any other questions? Yes?
So for these other chemical, I guess, stoichiometric compositions that you're getting, how do you know that those crystal structures aren't somewhat interesting?
So actually, what we've done is for this one, Hongyu actually suggested we just do some resistivity measurements just for the sake of curiosity. Nothing interesting has been found. And for the nickel-rich phase, we've just been told that or the literature has shown that heating for extended period of times and just cooling slowly actually results in magnesium losses in the formation of this nickel-rich phase. There's not been any studies so far to demonstrate any sort of, I don't know, interesting facet of this, but that's also another open venue for study.